For decades, scientists believed they understood what asteroids were made of, but when NASA finally brought samples back from asteroid Bennu, they found something that didn't fit that picture at all, a material that, according to current models, should not exist there. To understand why a robotic explorer would travel billions of kilometers to touch a small, dark rock, we first have to look down at the ground beneath our feet. Earth is a magnificent world. It is a planet of oceans, shifting continents, soaring mountains and deep valleys. It is alive with weather, biology, and the constant churning of geology. But this vitality comes at a cost. Earth is a master of reinvention. Rain washes away stone. Wind scours the plains. Volcanoes bury the past under new layers of lava. And plate tectonics slowly recycle the very crust of the planet, dragging old rock down into the mantle and melting it down. Earth is a recycler. It constantly erases its own history. If you wanted to know what the Earth was like on the day it was born, you would find almost no evidence left on the planet itself. The original materials, the pristine dust and gas that formed our world 4.5 billion years ago, have been cooked, crushed, mixed, and altered beyond recognition. To find our origins, we cannot look at the Earth. We have to look elsewhere. We have to look at the leftovers. Picture the solar system 4.5 billion years ago. Long before there were blue oceans or green forests, there was only a vast swirling cloud of gas and dust known as the solar nebula. It was a place of violent potential. Gravity, the great sculptor of the cosmos, began to pull this dust together. In the centre, the pressure grew immense, igniting a nuclear fire that became our sun. Around this new star, the remaining dust and rock began to collide and stick together. Pebbles became boulders, boulders became mountains, mountains became planetesimals. Through a chaotic game of cosmic billiards, these bodies smashed into one another, growing larger and hotter, eventually clearing their orbits to become the planets we know today. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But the process wasn't perfect. It wasn't clean. When the planets were finished forming, there was material left over. There were crumbs remaining on the table. These leftovers are the asteroids. Most of them drifted into the wide gap between Mars and Jupiter, settling into the stable rhythm of the main asteroid belt. Others were scattered into the icy depths of the outer solar system, while some were flung inward, crossing the paths of the rocky inner planets. Unlike the Earth, which has melted and changed, most asteroids have remained frozen in time. They are time capsules. They are the original bricks of the solar system, the unused construction materials that never made it into a planet. Because they're too small to have weather or geological activity, and because they drift in the vacuum of space, they have sat there, virtually unchanged, for billions of years. If you could pick up an asteroid and crack it open, you wouldn't just be holding a rock. You would be holding a piece of the original solar nebula. You would be holding the exact chemical recipe that existed before the Earth was formed. But not all asteroids are the same, and this is where the story gets interesting. Some asteroids are made of metal, the shattered cores of failed planets that were smashed apart in the early chaos. Some are made of stone, baked dry by the heat of the sun. But there is a third kind, a rarer and more precious kind known as the carbonaceous asteroid. These are the dark worlds. They are rich in carbon, the element that is the backbone of all life as we know it. They are often porous and fragile, more like clumps of dried mud than solid rock. And most importantly, scientists believe these dark asteroids contain water, not as liquid lakes, but locked away inside the crystal structure of clay minerals. This leads to a profound hypothesis, one that drives missions like OSIRIS-REx. When the Earth was first formed, it was likely a hot, dry ball of molten rock. It was a hellscape, inhospitable and barren. So where did our oceans come from? Where did the carbon that makes up our bodies come from? The leading theory suggests that long after the Earth cooled, it was bombarded by these primitive dark asteroids. It is possible that they acted as cosmic delivery trucks, crashing into our young planet and delivering the water that now fills our oceans and the organic molecules that eventually sparked the first life. This is why asteroids matter. They are not just hazards to be avoided or rocks to be mined, they are the silent storytellers of our genesis. They hold the answers to the questions we have been asking since we first looked up at the stars. Where did we come from? How did this happen? Are we alone? To answer these questions, we cannot just look at these rocks through telescopes. Light reflected off a surface can only tell you so much. To truly understand the story written in the stone, we have to go there. We have to reach out across the void, grab a piece of the beginning, and bring it home. And to do that, NASA chose a specific target, a small, spinning, pitch-black mountain of rubble named Bennu. Out of the millions of rocks drifting through our solar system, scattered in the vast belts between Mars and Jupiter, or frozen in the icy distance beyond Neptune. Why did scientists choose this one? Why, of all the celestial objects we could have visited, did we spend years hunting down a small charcoal black rock named Bennu? To answer that, we have to imagine looking for a shadow in the darkness. Bennu is not easy to find. For most of human history, it was completely invisible to us, hiding in the glare of the sun or lost against the black backdrop of deep space. It was only discovered in September of 1999, a faint pixel moving across the telescopes of the Linear Survey. But once we found it, we realized that Bennu was something special. It wasn't just another rock, it was a rare, pristine relic that had wandered remarkably close to home. If you were to approach Bennu in a spacecraft, as the OSIRIS-REx mission eventually would, the first thing you would notice is its darkness. Bennu is incredibly dark. In the language of astronomy, we talk about albedo, which is a measure of how much light an object reflects. A mirror has an albedo of 1.0, reflecting everything. The Earth, with its bright white clouds and ice caps, has an average albedo of about 0.3. Bennu has an albedo of roughly 0.4. It reflects only 4% of the sunlight that hits it. It is darker than a fresh layer of asphalt on a highway, darker than a piece of coal. If you were standing on its surface, looking down at your boots, the ground would look like a landscape of soot and shadows. This darkness is the first clue to its identity. Bennu is a carbonaceous asteroid, a Type B asteroid. That deep black colour comes from the presence of carbon, the same element that makes up graphite and, crucially, life itself. It tells us immediately that this world has not been heated or altered significantly since the dawn of the solar system. It is a raw, organic, rich clump of the primordial nebula. As you get closer, the shape of the asteroid resolves. It is not a sphere like a planet, nor is it an irregular potato shape like many other asteroids. Bennu looks distinctively like a spinning top. It is roughly diamond-shaped, with a pronounced bulge around its middle at the equator. This shape tells a violent story. Bennu is a rapid rotator spinning on its axis once every 4.3 hours. Over millions of years, this constant spinning has acted against the asteroid's weak gravity. It has pushed material from the poles down toward the equator, causing the asteroid's midsection to bulge outward. It is a landscape defined by centrifugal force, a world constantly trying to fling itself apart. In terms of size, Bennu is deceptively small compared to the planets we're used to. It has an average diameter of about 490 meters, roughly beyond 600 feet. To put that in human terms, it is slightly wider than the Empire State Building is tall. If you placed Bennu on Earth, it would comfortably cover a small neighborhood. In the grand scale of the cosmos, it is a speck of dust. But in the context of a space mission, it is a mountain floating in the void. It is large enough to have its own gravity, large enough to be a world with its own geography, its own north and south poles, and its own treacherous terrain. But perhaps the most important reason we chose Bennu is its location. Most asteroids live their lives in the main belt, far away from Earth. But Bennu is a wanderer. It is what we call a near-Earth object, or NEO. It belongs to a group of asteroids known as the Apollos, which cross Earth's orbit. Bennu doesn't stay in the safety of the deep solar system. It comes into our neighbourhood. It circles the Sun every 1.2 years on a path that occasionally brings it uncomfortably close to our own planet. This proximity makes Bennu a double-edged sword. On one hand, it is accessible. It is energetically cheap to send a spacecraft there compared to reaching Jupiter or Saturn. It is a neighbour we can visit. On the other hand, it is a threat. Bennu is considered one of the most hazardous asteroids currently known. Because its orbit crosses ours, there is a small but non-zero probability, about 1 in 2,700, that it could impact Earth late in the 22nd century, specifically around the year 2182. While those odds are low, the consequences of a 500-metre wide rock hitting Earth would be catastrophic, releasing more energy than all nuclear weapons tested in history combined. So, studying Bennu was not just a matter of scientific curiosity, it was a matter of planetary defence. We needed to understand the enemy. We needed to know its mass, its density, and how its orbit changes over time. But before the mission launched, before we saw the high-resolution images, we had a very specific mental image of what Bennu would look like up close. Based on our observations of other bodies like the Moon, scientists expected Bennu to be covered in regolith, a fine, sand-like dust created by billions of years of micrometeoroid impacts. We imagined vast smooth beaches of dark sand, rolling dunes where a spacecraft could easily descend and scoop up a sample without danger. We imagined a silent, smooth, black diamond drifting in the sun. We were right about the diamond shape. We were right about the darkness. But as we would soon discover, we were wrong about the texture. Bennu was not the smooth, sandy world we dreamed of. It was something far wilder, far rougher, and far more difficult to tame. It was a world of debris, a collection of rocks, boulders, and gravel that looked less like a solid planet and more like a ruin floating in zero gravity. It was a place where the temperature swings from boiling hot to freezing cold every 4 hours, cracking stones like eggshells. This was the target. A small, black spinning top, darker than coal, roughly the size of a skyscraper, drifting alone through the vacuum. It held the secrets of our origins locked inside its clay, minerals, and it held a potential threat to our future in its orbit. It was the perfect place to go. And so, we built a machine to go and meet it. To understand the machine we built, we first have to understand the limitations of looking. For centuries, astronomy was a science of observation. We were distant watchers, confined to the surface of our own planet, peering up through the distorting haze of our atmosphere. We built grand observatories on mountaintops and launched telescopes into orbit, collecting photons of light that had travelled across the void. We became experts at reading that light, analysing its colour and spectrum to guess what the universe was made of. But light has its limits. A telescope can tell you that an asteroid is dark. It can tell you that it reflects infrared light in a way that suggests the presence of clay or carbon. But it cannot tell you the precise isotopic ratio of the water locked inside those clays. It cannot put a grain of that asteroid under an electron microscope to see the atomic structure of an organic molecule. To truly answer the deepest questions about our origins, looking isn't enough. We need to touch. We need to hold the material in our hands. We need to bring it back to the laboratories on Earth, where we have instruments the size of buildings, synchrotrons and mass spectrometers that could never fit on a rocket. This was the driving force behind the mission. We didn't just want to visit Bennu, we wanted to bring a piece of it home. The mission was given a name that is a mouthful of a riddle: OSIRIS-REx. It stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. It is a dense acronym, but it maps out exactly what the spacecraft was designed to do. It was a mission to find our origins in the early solar system, to interpret the light reflecting off the asteroid to help us understand others like it, to identify resources like water that future astronauts might use, to provide security by measuring the forces that might push asteroids into Earth, and finally to be a regolith explorer, to dive into the loose soil of an alien world. There is also a poetic layer to the name. In ancient Egyptian mythology, Osiris was the god of the underworld and rebirth. He was a figure associated with both the fertile soils that allowed civilization to flourish and the mysteries of death. It was a fitting namesake for a mission travelling to an asteroid that could be a bringer of life, delivering water and organics to Earth, or a bringer of destruction. So, what does a machine built for such a task look like? OSIRIS-REx is not a sleek aerodynamic vessel from science fiction. It is a functional boxy workman of the void. Roughly the size of a delivery van, it is a cube of aluminum and honeycomb composite, wrapped in thermal blankets to protect it from the searing heat of the sun and the freezing cold of shadow. Sticking out from its sides are two large solar arrays, like wings, designed to catch the dim sunlight of deep space and convert it into the electricity that powers the brain of the ship. On one side, it carries a high-gain antenna, a large white dish that serves as its voice, beaming data back to Earth and listening for commands from its creators. But the true genius of OSIRIS-REx lies in its instruments. It is a robotic geologist. It carries a suite of cameras called OCAMs. These are the eyes of the mission, capable of seeing the asteroid as a tiny dot from millions of miles away, and then zooming in to see pebbles the size of a grain of sand on the surface. It carries laser altimeters to map the 3D shape of the rock, and spectrometers to sniff the chemical composition of the dust from orbit. However, the most critical piece of engineering, the heart of the entire mission, is a device known as TAG-SAM, the touch-and-go sample acquisition mechanism. Designing a tool to grab a sample from an asteroid is incredibly difficult. You cannot land on Bennu in the traditional sense. The gravity is so weak, only a few millionths of Earth's gravity, that landing gear would be useless. If you tried to land with shock absorbers, you might just bounce off and drift away forever. If you tried to use thrusters to hold yourself down, you would blow away the very soil you were trying to collect. So the engineers came up with a solution that was elegant in its simplicity. They built a pogo stick. TAG-SAM is essentially a robotic arm, 3 meters long, with a round collection head at the end that looks a bit like an enormous automotive air filter. The plan was not to land, but to kiss the surface. The spacecraft would slowly descend, tap the asteroid with the head of the arm, and then, in that split second of contact, it would fire a blast of nitrogen gas. It works like a reverse vacuum cleaner. Instead of sucking air in, it blows gas out. The blast of nitrogen churns up the dirt and rocks on the surface, creating a chaotic cloud of debris. The only place for that debris to go is up straight into the collection chamber of the TAG-SAM head. It is a violent moment of collection designed to happen in a calm, controlled 5 seconds. Touch, blast, collect, back away. This design philosophy, touch and go, defined the entire spacecraft. It meant OSIRIS-REx had to be autonomous. Bennu is so far away that a radio signal takes nearly 20 minutes to get there and back. A human pilot on Earth cannot steer the ship in real time. If the spacecraft senses a rock that is too high, or a slope that is too steep during its descent, it has to decide to abort the attempt on its own. It has to be smart. This was the idea behind OSIRIS-REx, a smart van-sized robot, armed with a high-tech pogo stick and a bottle of nitrogen gas, sent on a billion-kilometre journey to high-five a mountain of rubble. It was a concept of immense audacity, relying on thousands of systems working perfectly in a place where no mechanic could ever go to fix them. And in 2016, after years of design, testing and construction, the idea was finally ready to leave the drawing board and enter the sky. Space exploration begins with noise. It begins with fire, vibration, and a release of energy so violent that it shakes the ground for miles around. But this violence is temporary. It is merely the price of admission. the energy required to tear a machine away from the grip of gravity. Once that price is paid, the noise stops, the fire goes out, and the spacecraft enters the state that will define the rest of its life: silence. For OSIRIS-REx, the noise began on the evening of September 8, 2016. The setting was Cape Canaveral, Florida. An Atlas IV rocket stood on the launch pad, glowing white under the floodlights, breathing vents of cryogenic oxygen into the humid air. Inside the fairing at the very top sat the spacecraft, folded up like an intricate piece of origami, waiting for the moment of release. At 7:05 p.m. local time, the engines ignited. The rocket rose from the coast, turning into a bright arc of fire over the Atlantic Ocean. For a few minutes it fought the thick atmosphere of our planet, climbing higher and faster until the blue sky faded into the black of space, and then, with a final push, the upper stage engine cut off. The spacecraft separated. It was free. But it was not yet on its way to Bennu. Not really. Space travel is rarely a straight line. You cannot simply point your ship at a target and fire the engines, like driving a car down a highway. Orbital mechanics is a game of curves and momentum. Bennu spins on an orbit that is tilted by about 6 degrees relative to Earth's orbit. To reach it, OSIRIS-REx didn't just need speed, it needed to change the angle of its entire existence. It needed to lift itself out of the flat plane of the solar system where Earth resides. Doing this requires an immense amount of energy, more fuel than a rocket of that size could carry. So, the mission planners used a trick that has become a staple of deep space navigation. They decided to steal the energy from Earth itself. For the first year of its mission, OSIRIS-REx didn't go to the asteroid. It just circled the Sun, tracing a loop that looked almost exactly like Earth's orbit. It was a phantom year, a lap around the track designed to bring it right back to where it started. 1 year later, in September 2017, the spacecraft returned to us. It approached Earth from behind, dropping down over the Antarctic, skimming just 17,000 kilometers above the surface of our planet. This was the gravity assist. By diving into Earth's gravity well and swinging around it, the spacecraft used the planet as a gravitational slingshot. It stole a tiny fraction of Earth's orbital momentum, an amount so small it didn't affect our planet's path around the Sun by even the width of an atom. But for the small spacecraft, it was everything. The maneuver acted like a giant hand, tilting the spacecraft's orbit upward, throwing it out of the ecliptic plane and putting it on the perfect intercept course for Bennu. As it flew away from Earth for the second and final time, OSIRIS-REx turned its cameras back. It took a picture of our home, a beautiful, fragile blue marble suspended in the dark, with the moon standing quietly beside it. It was a farewell portrait. The next time the spacecraft would see Earth, 7 years later, it would be as a returning traveller carrying a piece of an alien world. After the gravity assist, the mission entered the cruise phase. This is the part of space travel that movies often skip. It is the long, uneventful drift through the void. For nearly a year there was nothing to see. No planets, no asteroids, no landmarks. Just the static field of stars that never changes, no matter how fast you're moving. The spacecraft was travelling at tens of thousands of kilometres per hour, but without any air to rush past it, without any vibration from the road, there was no sensation of speed. If you were sitting on the solar panels, you would feel perfectly still. You would be floating in a silent, endless night. During this time, the spacecraft was asleep, in a manner of speaking. Most of its instruments were turned off to save power. The team on Earth checked in regularly, sending pings to ensure the heart was still beating, the heaters were still warming the electronics, and the antenna was still pointed toward home. But mostly, it was a time of waiting. A time of quiet transit across the cold gap between worlds. Then, in August 2018, The silence changed. The spacecraft was finally close enough to open its eyes. The Polycam, the mission's long-range telescope, snapped a series of images of the star field ahead. The navigation team on Earth analysed the photos, looking for a speck of light that moved differently from the background stars, and there it was, Bennu. At that distance, roughly 2 million kilometres away, the asteroid was nothing more than a single pixel. It was a faint dot indistinguishable from the thousands of stars around it, except for its motion. But that dot was the destination. It was the mountain the machine had been sent to climb. This marked the beginning of the approach phase, a slow-motion braking manoeuvre that would last for months. This is another aspect of spaceflight that defies intuition. In movies, spaceships zoom up to a planet and park instantly. In reality, rendezvous is a delicate, terrifying dance of physics. OSIRIS-REx was moving at incredible speeds relative to the Sun. To enter orbit around Bennu, it had to match the asteroid's speed and direction perfectly. If it came in too fast, it would fly right past and miss the target forever. If it came in too slow, it wouldn't catch up. The spacecraft fired its thrusters in a series of careful braking burns, shedding velocity inching closer and closer. As the weeks passed, the dot grew. It became a blob, then a shape. By November, the spinning top form of Bennu became visible. The single pixel resolved into a world. But even then, from a distance, it looked smooth. The low-resolution images showed a diamond-shaped rock that appeared consistent with the scientists' predictions. It looked manageable. It looked like the sandy, beach-covered world they had built their machine to conquer. The team on Earth watched the screen with growing anticipation. They were about to transition from astronomy, studying a point of light, to geology, studying a landscape. They were about to see the face of the asteroid for the first time. The spacecraft drifted closer, the cameras clicking away, capturing the asteroid as it rotated in the sunlight. The silence of the cruise was over. The mission had arrived. And as the first high-resolution images began to download, pixel by pixel, layer by layer, the anticipation in the control room would turn into something else entirely. They were about to realize that the map they had in their heads was wrong. The beach they had come to find wasn't there. On December 3rd, 2018, the long commute came to an end. After travelling more than 2 billion kilometres, looping around the Sun, stealing energy from the Earth, and drifting through the silent void for over 2 years, OSIRIS-REx finally arrived at its destination. The approach to an asteroid is not like the dramatic landings we see in cinema. There is no roar of engines fighting against an atmosphere, no heat shields glowing red, no sudden jolt of touchdown. Instead, it is a moment of quiet, mathematical precision. It is the moment when a spacecraft matches its speed so perfectly with its target that the two objects effectively become one system, locked together in a slow celestial dance. But as the spacecraft drew closer and the cameras began to resolve the details of the surface, the mood in the Mission Control Center shifted from celebration to shock. For years, the mission planners had a very specific image of Bennu in their minds. Based on thermal data collected from telescopes on Earth and in space, they had built a model of what the surface should look like. The data suggested that Bennu was covered in regolith, loose soil, gravel and sand. They expected vast open stretches of smooth terrain. They imagined dusty plains, perhaps dotted with a few rocks, but largely flat, like a beach at twilight. These beaches were essential. The spacecraft was about the size of a van, and its sampling arm needed a clear, safe area roughly 50 metres wide, half a football field, to descend and touch the surface without hitting anything dangerous. But as the high-resolution images streamed back to Earth, revealing the asteroid's face in sharp detail for the first time, that dream of a sandy beach evaporated. Bennu was not smooth. It was a chaotic, rugged, violent mess. From pole to pole, the asteroid was covered in boulders. It was a world of debris. There were rocks the size of cars, rocks the size of houses, and immense boulders the size of office buildings, all jumbled together in a terrifying pile. It looked less like a planet and more like a construction site that had been abandoned in the middle of a demolition. There were no smooth plains, there were no wide-open beaches. Every square metre of the surface seemed to be choked with jagged hazards. The team realised almost instantly that the 50-metre parking spot they had designed their entire mission around simply did not exist. They had brought a machine built for a beach to a world made of mountains, but before they could solve the problem of how to touch the surface, they first had to solve the problem of how to stay there. Orbiting Bennu presented a challenge that was unique in the history of spaceflight. We're used to thinking of gravity as a powerful force, the force that holds our feet to the ground and keeps the moon tethered to the Earth. But Bennu is tiny. It is only about 500 meters wide. Its mass is so small that its gravity is almost non-existent. The gravitational pull on the surface of Bennu is about 100,000 times weaker than Earth's gravity. To put that in perspective, if you were standing on Bennu, you would weigh roughly as much as a sheet of paper. If you were to walk at a normal pace, you would launch yourself off the surface and drift away into space, never to return. You could effectively jump into orbit with a slight bend of your knees. For a spacecraft, this environment, known as microgravity, is incredibly difficult to navigate. In a strong gravity field like Earth's or Mars, an orbit is a sturdy thing. Gravity grabs you and holds you in a curve. But at Bennu, the gravity is so faint that other, subtle forces start to take over. The pressure of sunlight hitting the spacecraft's solar panels, a force so weak we never notice it on Earth, was enough to push OSIRIS-REx off course. The slight unevenness of the asteroid's gravity field, caused by the lumpy distribution of those massive boulders, tugged at the ship in unpredictable ways. Even the heat radiating off the asteroid's surface acted like a gentle wind, blowing the spacecraft away. Navigating around Bennu was less like orbiting a planet and more like docking a boat in a very slow, very gentle current. To stay in orbit, OSIRIS-REx had to move incredibly slowly. If it moved too fast, it would break free of the asteroid's weak grip. So, the spacecraft entered a frozen orbit. It travelled at a speed of only a few centimetres per second. Imagine a snail moving across a sidewalk. That is roughly the speed at which OSIRIS-REx orbited Bennu. It took days to complete a single revolution. It was a slow-motion ballet performed in total silence. On December 31, 2018, the spacecraft fired its thrusters for a precise 8 seconds, slipping into this delicate orbit. In doing so, it broke the record for the smallest object ever orbited by a spacecraft. It was floating just over 1.5 kilometers from the centre of the asteroid, closer than any ship had ever orbited a celestial body. From this vantage point, the view was spectacular and intimidating. The asteroid filled the camera's field of view, a spinning diamond of darkness against the stars. The shadows on the surface were long and sharp, stretching out from the thousands of boulders that littered the landscape. Because there is no atmosphere on Bennu to scatter light, there is no softness to the image. Everything is high contrast. A rock is either blazing in the harsh white light of the sun, or hidden in absolute ink-black shadow. There is no grey. There is no twilight. As the spacecraft drifted silently over this alien terrain, the team on Earth began to catalogue the features below. They saw the gargoyle, a massive boulder jutting out near the equator. They saw Benben Saxum, a towering rock standing high on the southern hemisphere, casting a long shadow over the rocky fields. They saw a world that was hostile to their presence, a world that looked like it would defend its secrets with jagged teeth. The arrival at Bennu was a triumph of navigation, but it was also a moment of reckoning. The easy mission was gone. The spacecraft was healthy, the orbit was stable, and the view was breathtaking, but the question hung heavy in the control room. In a world made entirely of hazards, where do you safely land a machine worth $1 billion? The team realised they would have to rewrite the rulebook. They couldn't just look for a parking spot. They would have to map every single rock, pebble and crater on the entire world. They would have to learn to live with this rubble pile, to understand its strange microgravity physics, and to find a needle of safety in a haystack of danger. The exploration had begun, but the challenge was far greater than anyone had imagined, and as they watched the asteroid spin beneath them, they began to notice something else, something even stranger. Bennu wasn't just a dead rock, it was moving, it was shedding, it was alive. To understand what it is like to be close to Bennu, you have to unlearn everything you know about rocks. On Earth, a rock is a solid, stubborn thing. A mountain is immovable. If you drop a stone, it falls. If you step on the ground, it holds you. But Bennu is not a solid world. It is something far more fragile and strange. Scientists call it a rubble pile, but that term feels too messy for something so elegant. Imagine 1 billion rocks, pebbles, and boulders floating together in the dark, held in a loose spherical swarm by nothing more than their own mutual whisper of gravity. It is not a single stone, it is a droplet of gravel. For the first few weeks in orbit, the OSIRIS-REx spacecraft treated Bennu like a static object, a dead stage upon which to perform its mission. But on January 6, 2019, the asteroid woke up. The navigation cameras, which were constantly scanning the star fields to keep the spacecraft oriented, picked up something that shouldn't have been there. In the black space just above the asteroid's surface, there were bright specks. They looked like stars, but they were in the wrong place. Upon closer inspection, the team realized they weren't stars at all. They were rocks. Bennu was spitting pieces of itself into space. It was an active asteroid. Small explosions of pebbles were popping off the surface, launched by mechanisms we still don't fully understand. Perhaps the release of water vapor, or the sudden cracking of rocks under thermal stress. Most of these pebbles would drift up, loop into orbit for a few days like tiny temporary moons, and then rain back down onto the surface. But some had enough speed to escape forever, lost to the void. This discovery changed the way we saw the asteroid. It wasn't just a heap of debris, it was a dynamic, restless environment. It was shedding. Living with a rubble pile meant living with constant, subtle motion. Because Bennu is not a solid fused object, its insides are likely porous, filled with voids and gaps. If you could stomp your foot on the surface, the vibrations wouldn't just ring through the crust. They would be dampened and absorbed, the energy dissipating into the loose shifting sands below. This looseness creates a terrifying possibility for a visitor. The surface of Bennu is less like solid ground and more like a ball pit. The rocks aren't cemented into a crust, they are just resting there. The friction between them is the only thing stopping the whole world from behaving like a fluid. And then there is the sound, or rather the sound of temperature. Bennu spins rapidly, completing a full day every 4.3 hours. Because it has no atmosphere to trap heat, the temperature swings are brutal. In the sunlight, the rocks bake at over 100 degrees Celsius. 2 hours later, in the dark, they freeze at minus 70 degrees. This rapid cycling creates a phenomenon called thermal fatigue. It is a slow-motion violence. The rocks expand in the heat and contract in the cold, over and over, thousands of times a year, for millions of years. Eventually they give up. They crack. The spacecraft's cameras saw evidence of this everywhere. Boulders split cleanly in half, and rocks exfoliating like onions, shedding their outer layers in flakes. This process acts like a planetary mill, slowly grinding the large boulders down into smaller rocks, and the rocks into pebbles, and the pebbles into dust. It is the only erosion this world knows, but perhaps the most profound force acting on Bennu is light itself. We don't often think of light as having a push. If you shine a flashlight on your hand, you don't feel it press against you, but light carries momentum. Over vast timescales, and on small bodies with weak gravity, sunlight becomes a powerful engine. This is known as the Yarkovsky effect. As Bennu rotates, the sun heats up one side. As that side turns into the darkness of night, the rocks radiate that heat back out into space as thermal energy. This escaping heat acts like a tiny, constant thruster. It pushes against the asteroid. It is a microscopic force, but it is relentless. Over millions of years, this pressure from sunlight has pushed Bennu, drifting it inward from the main asteroid belt toward Earth. It is sunlight that turned Bennu into a wanderer. There is also a related force called the Yorp effect. The sunlight doesn't just push the asteroid. Because of Bennu's lumpy, uneven shape, the light hits angled surfaces like wind hitting a windmill. It is slowly spinning the asteroid up. Bennu is accelerating. Its rotation is getting faster by about 1 second every century. That sounds negligible, but for a rubble pile, it is a death sentence. As it spins faster, the centrifugal force at its equator grows stronger. There is a cohesion limit, a speed at which the gravity holding the rocks together is overpowered by the force trying to fling them apart. Bennu is perilously close to that limit. It is bulging at the waist because it is trying to fly apart. If it spins much faster, rocks will start to lift off the equator and drift into space, dismantling the world piece by piece. Orbiting Bennu meant understanding all of these forces. The OSIRIS-REx team had to navigate a spacecraft around a world that was spitting rocks, cracking under thermal stress, behaving like a fluid, and slowly spinning itself to death in the sunlight. It was a chaotic, beautiful, dangerous place. And somewhere in that mess of shifting boulders and thermal cracking, the team had to find a place to touch. They had to find a patch of calm in the middle of the storm. But as the mapping campaign continued, scanning the surface meter by meter, the reality set in. The calm patch didn't exist. The map was full of red flags. The rubble pile offered no sanctuary. By the spring of 2019, the OSIRIS-REx mission faced a crisis of abundance. The spacecraft was healthy, the cameras were working perfectly, and the asteroid was mapped in higher resolution than any other object in the solar system. The team had too much data, but they had nowhere to go. The mission had been designed around a simple geometric assumption that somewhere on the surface of Bennu there would be a pond. They were looking for a circle of fine-grained material, sand or gravel small enough to fit inside the sampling head, that was at least 50 meters wide. That was the safety margin engineered into the spacecraft's navigation system. A 50-meter radius meant that even if the spacecraft drifted slightly off course during its descent, it would still land on safe, flat ground. But as the team scanned the global map of Bennu, searching from the North Pole to the south, they found 0 sites that met this criteria. There were no ponds. There were no 50-meter clearings. The largest patches of safe material they could find were barely 5 or 10 meters wide, tiny pockets of gravel surrounded by jagged, towering boulders. This was not just a navigation problem. It was an existential threat to the mission. The spacecraft's guidance system, designed years earlier on Earth, simply wasn't precise enough to hit such a small target. It was like trying to park a van in a garage that was only 1 inch wider than the vehicle, using a remote control from 1 billion kilometers away. The team had to make a choice. They could not change the asteroid, so they had to change the machine. In a feat of remote engineering, they rewrote the spacecraft's navigation software while it was flying in deep space. They moved away from the original LiDAR-based guidance system and developed a new method called natural feature tracking. They taught OSIRIS-REx to see. Instead of just measuring distance, the spacecraft would now take real-time images during its descent, comparing them to a catalogue of known landmarks, rocks, craters, and shadows stored in its memory. It would triangulate its position constantly, predicting where it would touch down. If the computer realized it was drifting off course by even a few feet, it would autonomously abort the landing and fly away. With this new bullseye capability, the target radius shrank. They didn't need 50 meters anymore. They could aim for a site the size of a few parking spaces. With the new software ready, the search began in earnest. The team divided the asteroid into a grid, counting rocks, measuring slopes, and analysing the temperature of every square inch. They narrowed the candidates down to 4 potential sites. Following the theme of the mission's Egyptian mythology, they named these sites after birds found in Egypt: sandpiper, osprey, kingfisher, and nightingale. Each site had its own personality and its own dangers. Sandpiper was located in the southern hemisphere, nestled inside a relatively flat crater, but it was surrounded by walls of rock that limited the approach angles. Kingfisher was near the equator, rich in the hydrated minerals they wanted, but it sat in a region filled with small, hazardous rocks that could jam the sampling mechanism. Osprey was a promising backup located near the North Pole, but the material there looked tougher, more bedrock-like, which might be hard to scoop up. And then there was Nightingale. Located high in the northern latitudes, Nightingale sat inside a small young crater. Because it was so far north, it was a place of perpetual cool shadows. This was scientifically perfect. The darkness meant the material there had been protected from the harsh weathering of the sun. It was likely the most pristine, carbon-rich, organic-filled dust on the entire asteroid. It was exactly the kind of black gold the scientists had travelled all this way to find. Furthermore, the images showed that the crater floor was covered in fine-grained material. It wasn't a solid slab of rock. It was a bed of gravel, dark and loose, perfect for the tagsome head to penetrate. But Nightingale was also a trap. It was the most scientifically valuable site, but it was also the most dangerous. The safe zone in the centre of the crater was only about 6 meters wide. That is roughly the size of a small bedroom. To make matters worse, the crater was guarded. Looming on the eastern rim of the Nightingale crater was a massive pointed boulder. It was a jagged monolith the size of a 2-story building. The team nicknamed it Mount Doom. If the spacecraft tipped its solar panels too far during the descent, it could clip the side of Mount Doom. If it backed away incorrectly after the sample collection, it could crash into it. The margin for error was razor thin. The choice was agonizing. Do you go to a safer site like Osprey, where the material might be harder to collect and less scientifically rich? Or do you gamble the entire mission on Nightingale, risking the destruction of the spacecraft for the chance to get the perfect sample? The debate continued for months. They modelled every trajectory. They simulated thousands of landing attempts. They analysed the lighting conditions, checking to see where the shadows would fall on specific dates. In the end, the science won. On December 12, 2019, NASA announced the decision. The primary target would be Nightingale. The selection of Nightingale transformed the mission. It was no longer a broad exploration. It became a sniper shot. The team spent the next year obsessing over that single 6-meter patch of gravel. They mapped every rock inside the crater down to the centimetre. They knew the shape of every shadow. They knew the height of Mount Doom to the inch. They weren't just visiting an asteroid anymore. They were visiting a specific room in a specific house on that asteroid. The stage was set. The software was updated. The target was locked. But as the date of the attempt drew closer, the reality of what they were about to do began to sink in. They were going to drop a robot, untethered and alone, into a pit of shadows, asking it to thread the needle between a wall of rock and a building-sized boulder, to kiss the ground for 5 seconds and escape before the gravity or the spinning terrain could claim it. There would be no joystick, no human pilot to correct a mistake. Once the command was sent, the descent would happen in radio silence. The team on Earth would only know if they had succeeded or if they had crashed. 20 minutes after it was already over. They had chosen their place to touch. Now, they just had to stick the landing. On October 20th, 2020, the waiting ended. After 4 years of travel, 2 years of mapping, and months of rehearsal, the moment of contact had finally arrived. The spacecraft was millions of kilometers away, floating in the silence of deep space. Back on Earth, the mission control team in Denver, Colorado could do nothing but watch. The command sequence had already been uploaded. The radio signals travelling at the speed of light took 18.5 minutes to cross the gap between Earth and Bennu. This meant that whatever was happening on the screen had already happened nearly 20 minutes ago. The spacecraft was effectively a ghost, acting out a memory. The descent began with a gentle pulse of the thrusters. OSIRIS-REx broke its safe, frozen orbit and began the slow fall toward the surface. This was not a dive, it was a drift. The spacecraft moved at a speed of about 10 centimeters per second, slower than a gentle walking pace, slower than a snowflake falling in still air. To prepare for this moment, the spacecraft had transformed. Its two large solar arrays, which normally extended flat out to the sides like wings, were tilted upward into a Y-wing configuration. This wasn't for aerodynamics, there is no air in space, but for clearance. The team knew they were descending into a crater surrounded by jagged rocks. By lifting its wings, the spacecraft made itself narrower, pulling its fragile power source away from the looming threat of the boulders. For 4 hours the machine descended alone. Inside its computer brain, the natural feature tracking software was running a feverish comparison. The cameras were snapping photos of the approaching ground and matching them against the hazard map stored in its memory. It was looking for landmarks, familiar rocks, specific shadows, triangulating its position in real time. If it calculated that it was drifting even a few feet outside the safe zone of Nightingale, it was programmed to abort. It would fire its engines and flee back to safety without asking for permission. But it didn't abort. The green, safe path remained clear. As the spacecraft dropped lower, the crater walls of Nightingale began to rise up around it. To the east, the jagged peak of Mount Doom cast its long, cold shadow over the site. The target circle was barely the size of a few parking spaces, a tiny patch of dark gravel surrounded by ruin. At an altitude of 50 meters, the spacecraft performed the checkpoint burn, adjusting its trajectory. At 25 meters, it performed the matchpoint burn. This was the critical moment where it synchronized its motion with the asteroid's rotation. Bennu was spinning beneath it, but for the spacecraft, the ground suddenly appeared to freeze. It was hovering, matching the spin perfectly, descending vertically relative to the surface. The camera view showed the ground rushing up, a chaotic jumble of black rocks and grey dust. The tagsam arm, the 3-meter-long pogo stick, was extended and locked, ready to take the blow. Then contact. The sampling head struck the surface. What happened next was not what anyone expected. Based on Earth mechanics, you would expect a collision. You would expect the arm to hit the ground, resist, and perhaps bounce slightly as the spacecraft's momentum was absorbed by the rock. But Bennu didn't fight back. When the head touched the gravel, there was no resistance. It was like punching a fist into a bull pit. The arm didn't bounce, it sank. The surface was so loosely packed, held together by such faint gravity, that it behaved more like a fluid than a solid. The heavy metal head punched through the outer layer of pebbles and kept going, plunging deep into the asteroid's subsurface. In that fraction of a second, as the arm was burying itself in the ground, the spacecraft fired its weapon. A bottle of compressed nitrogen gas exploded through the nozzle at the end of the arm. The blast was designed to stir up dust, but in this fluid, microgravity environment, it created a catastrophe of debris. The gas expanded violently, blowing a massive crater into the loose material. Rocks, dust, and gravel were blasted upward, straight into the open mouth of the collection chamber. The spacecraft, sensing the contact, was programmed to wait for just a moment before fleeing. But it was still sinking. The momentum of the van-sized vehicle was driving it deeper and deeper into the asteroid. For a terrifying second, it seemed as if the asteroid might swallow the machine whole. Then, the back-away burn triggered. The main thrusters fired, pushing the spacecraft backward. But because the arm was buried so deep and the gravity was so weak, the thrusters didn't just push the ship up, they blasted the surface below. The exhaust plumes churned the rubble pile even further, creating a chaotic wall of expanding debris. Slowly, agonizingly, the machine reversed its fall. It pulled its arm out of the soil, dragging a cloud of rocks with it, and began to climb back into the black sky. On Earth, 18 minutes later, the telemetry data arrived. The flight controllers saw the signals change. They saw the accelerometer spike from the contact. They saw the pressure drop in the nitrogen bottle. They saw the thrusters fire for the retreat. "Touchdown declared," the voice came over the loop. "Sampling is in progress." And then, "Sample collection is complete. Back-away burn executed." The room erupted in applause, but it was a celebration tempered by the delay. They knew the robot had touched the asteroid. They knew it had fired the gas, but they couldn't see it yet. They had to wait for the images to trickle back across the void. When the pictures finally arrived, they revealed the violence of the encounter. They showed the arm plunging into the dark surface, the sudden explosion of rocks that completely obscured the camera's view, and the chaotic retreat. It was a messy, chaotic smash and grab. OSIRIS-REx had punched an asteroid in the face. The spacecraft was safe, drifting away from Bennu, its arm clutching a precious cargo. But as the dust settled and the cameras inspected the sampling head, the team realized the encounter had been perhaps too successful. The head was designed to catch rocks, but it was absolutely stuffed. The touch and go was over. The quiet journey had culminated in 5 seconds of controlled chaos. Now, the question wasn't if they had collected a sample. The question was, had they collected too much? In the hours following the touch-and-go maneuver, the euphoria of success was quickly replaced by a new, urgent anxiety. OSIRIS-REx had done its job. It had descended into the crater, fired its gas bottle, and retreated safely. But as the spacecraft moved to a safe distance and turned its cameras on the collection head to inspect the prize, the images revealed a problem. The mission had been too successful. The blast of nitrogen gas had been so effective in the fluid-like rubble of Nightingale that it had churned up a massive volume of material. The collection head, designed to hold up to 2 kilograms of rocks, was absolutely stuffed. It was overflowing. The images showed a terrifying sight for the engineers. The mylar flap designed to seal the canister was jammed open. Large rocks were wedged in the mechanism, preventing it from closing. And through the gaps, precious particles of Bennu were drifting out into the vacuum of space. The spacecraft was bleeding. Every time it fired a thruster or moved slightly, more dust was lost. The original plan had called for a leisurely series of maneuvers. The team had planned to spin the spacecraft to measure the mass of the sample before stowing it. But that plan was scrapped instantly. There was no time for measurements. Speed was now the only priority. They had to get the sample inside the return capsule and seal it shut before any more of the asteroid was lost. Over 2 tense days in late October 2020, the team commanded the spacecraft to perform the stowing sequence. It was a delicate, slow-motion operation performed by a robot millions of kilometers away. The arm had to articulate perfectly, placing the leaking head into the sample return capsule. The latches had to click. The seal had to hold. When the confirmation finally came down that the head was secured and the capsule was sealed, the control room could finally breathe. The cargo was safe. The leak had stopped. But OSIRIS-REx wasn't ready to leave just yet. It remained in the vicinity of Bennu for another 6 months, waiting for the celestial mechanics to align. The planets had to be in the right position for the transfer. Finally, on May 10th, 2021, the main engines fired. There was no fanfare in space, just a silent push of hydrazine. The spacecraft broke its bond with the asteroid's weak gravity and began the long drift back toward the sun. Bennu, the small dark diamond that had been its entire world for 2.5 years, slowly shrank into the distance. It became a shape, then a blob, and finally returned to being just a single pixel of light among the stars. The journey home took 2.5 years. It was a mirror image of the journey out, another long, silent cruise through the emptiness, but this time the The spacecraft carried a secret. Tucked inside its belly, inside a heat shield, inside a sealed canister, was a piece of the early solar system. Fast forward to September 24th, 2023. The spacecraft was approaching Earth, but OSIRIS-REx itself would not be landing. Its job was to act as a courier. It was coming in hot, aiming for a specific patch of desert in the United States. 4 hours before entering the atmosphere, the spacecraft released the sample return capsule. With a mechanical shove, it tossed the capsule toward Earth. Then the main spacecraft fired its thrusters to divert its own path, skipping off the atmosphere to continue its life as a wanderer in the solar system. The capsule was now alone. It was a small, saucer-shaped object, no bigger than a car tire, hitting the atmosphere at over 44,000 kilometers per hour. This was the most violent phase of the entire 7-year mission. For minutes, the capsule was engulfed in a fireball. The air in front of it was compressed into a shock wave so intense it turned into plasma. The heat shield glowed searing orange, ablating away layer by layer, sacrificing itself to protect the cool darkness inside. Back on the ground in the high desert of Utah, recovery teams watched the sky. The Department of Defense radars tracked the incoming object, and then the infrared cameras picked it up, a bright streak tearing across the blue morning sky. At an altitude of about 32 kilometers, the drogue parachute deployed to stabilize the spin. Then, at about 1.5 kilometers, the main parachute unfurled. This was the moment of truth. In a previous mission years earlier, the Genesis mission, a parachute failure had caused a sample capsule to smash into the ground. Everyone held their breath, but the orange and white canopy blossomed perfectly. The capsule slowed. The roar of re-entry faded into the gentle flapping of nylon in the wind. It drifted down over the Utah test and training range, a vast, quiet expanse of salt flats and sagebrush. At 8:52 a.m. local time, it touched the ground. It didn't crash. It didn't roll. It just landed with a dull thud, sitting upright in the sand as if it had been placed there by hand. The recovery helicopters swooped in. The team, dressed in hazardous material suits to protect the sample from earthly contaminants, approached the charred saucer. They checked for leaking gases. They measured the temperature. It was over. The loop was closed. A journey that began with a rocket launch in Florida, that circled the sun, that danced with a rubble pile in deep space, that punched an asteroid and bled dust into the void, had ended in a quiet patch of desert sand. The spacecraft was gone, sailing off to visit another asteroid named Apophis. But the treasure was here. The team carefully lifted the capsule. It was wrapped in protective sheets and flown by helicopter to a temporary clean room nearby. They knew they had something. They knew the mission was a success, but they still didn't know exactly what was inside. They didn't know that the black dust in that canister was hiding a white secret, a chemical clue that would confuse and delight them, forcing them to rethink the history of the rock they had just left behind. The canister was loaded onto a plane and flown to Houston. The long way home was finished. Now the science could begin. The journey was over, but the mystery was just beginning. In a pristine white laboratory at the Johnson Space Center in Houston, Texas, a team of curators dressed in white protective suits prepared to open the treasure chest. This was not a quick process. The sample canister had been sealed in the vacuum of space, and opening it on Earth required a level of care that bordered on obsession. The air in the room was filtered to remove even the tiniest speck of Earth dust. The tools were sterilized. The atmosphere inside the handling glove box was pure nitrogen, ensuring that the alien rocks would never touch our corrosive, oxygen-rich atmosphere. When they finally disassembled the return capsule and reached the tagsome head, the mechanism that had touched the asteroid, they encountered their first problem. The fasteners were stuck. The head was so full of material, packed so tightly with dust and rocks from the explosive sampling event, that it was difficult to take apart. The team had to spend weeks designing new tools and techniques just to pry it open without contaminating the sample. It was a slow, agonizing striptease of scientific discovery. But even before they got the main head open, they found dust everywhere. The interior of the canister was coated in a fine, dark soot. There was so much bonus material spilled outside the collection head that the scientists had plenty to work with while they struggled with the stuck fasteners. When the main bulk of the sample was finally revealed, it was breathtaking. It was a mound of charcoal black gravel, arguably the most precious dirt on Earth. They had hoped to collect 60 grams of material. They had brought back 121.6 grams. It was a massive haul. The initial analysis confirmed what the mission had promised. The material was incredibly rich in carbon, about 4.7% by weight. It was loaded with hydrated clay minerals, proving that water had been a major player in Bennu's history. It contained organic molecules, the complex carbon chains that are the precursors to life. For the scientists, this was a triumph. They were holding the pristine leftovers of the solar nebula. But then they saw something else. Amidst the sea of pitch-black rocks and dark dust, there were bright white fragments. They stood out like diamonds in a coal mine. At first, the team was confused. Bennu is one of the darkest objects in the solar system. Where did this bright white material come from? Was it contamination? Was it a piece of the spacecraft that had broken off during the violent sampling event? They took these white flakes and put them under the electron microscopes. They bombarded them with X-rays to read their atomic structure. They waited for the chemical signature to come back. The answer, when it arrived, didn't make sense. The white material was magnesium sodium phosphate. This might sound like a dry chemical name to a layperson, but to a geochemist, it was a bombshell. Phosphates are not uncommon in space. Phosphorus is a key element for life. It is the P in DNA and RNA, and the backbone of ATP, the energy molecule of all living cells. But finding it in this specific form, magnesium sodium phosphate, was startling. Here is why it shouldn't have been there. This specific mineral is water-soluble. It doesn't form in the vacuum of space. It doesn't form in dry rock. It forms when you have liquid water, and not just a drop of dampness, but a lot of water. It implies a dynamic, fluid-rich environment where water can dissolve minerals, concentrate them, and precipitate them out. On Earth, we sometimes find similar minerals in evaporated lake beds, or even in biological processes. But Bennu is a small, dry, airless pile of rubble floating in a vacuum. It has no lakes, it has no oceans, it has no atmosphere. So how did a mineral that requires an ocean end up on a dry rock in deep space? The presence of the phosphate crust forced the scientists to rewrite the history of the asteroid. Bennu, they realized, is not a whole world. It is a fragment. It is a piece of shrapnel from a much larger, ancient catastrophe. Billions of years ago, in the dawn of the solar system, there was likely a much larger parent body. A protoplanet, perhaps, 100 kilometers wide or more. This parent world was large enough to have internal heat. It was large enough to melt ice into liquid water. The discovery of the phosphates suggests that this parent world was an ocean world. It didn't have oceans on the surface like Earth. It had hydrothermal systems underground. Picture the floor of Earth's oceans, where hot vents spew mineral-rich water into the cold dark. The parent body of Bennu likely had similar plumbing. Hot, salty, chemically active water, circulating through cracks in the rock, dissolving elements like sodium and phosphorus, and depositing these white crusts inside the fractures. It was a wet, warm, chemically active womb, possibly containing all the ingredients necessary for life. Then, disaster struck. Sometime in the chaotic history of the solar system, this parent ocean world was smashed apart. A massive collision with another asteroid shattered it. The water boiled away into space. The rocks were scattered. Over time, gravity pulled some of those shattered pieces back together. The dry, broken shards of that lost ocean world drifted into a clump, forming the rubble pile we now call Bennu. The white phosphate crusts are the fossilized remains of that ancient plumbing system. They are the dried-up scum from a bathtub that was drained billions of years ago. This discovery changes everything. It means that when OSIRIS-REx touched Bennu, it wasn't just touching a rock. It was touching the ruins of a lost ocean. It suggests that these ocean worlds might have been common in the early solar system. It also strengthens the theory that asteroids like Bennu were the delivery mechanisms for Earth. If rocks like this are covered in water-soluble phosphates and organic molecules, and if thousands of them rained down on the early Earth, they wouldn't just have delivered water, they would have delivered a pre-packaged starter kit for biology. Bennu was carrying the chemistry of life, frozen in stone, waiting for a home. The impossible material wasn't a mistake, it was a message. It told us that the dry, dark rocks of the asteroid belt were once wet and dynamic, and it reminded us that in planetary science, things are rarely as simple as they appear on the surface. To find the ocean, you sometimes have to sift through the dust. We study history to understand where we came from, but we study physics to ensure we have a future. While the discovery of ancient oceans and organic molecules tells us the story of our past, the OSIRIS-REx mission had another, darker purpose. It wasn't just an archaeological dig, it was a reconnaissance mission. Because Bennu is not just a time capsule, it is also one of the most dangerous rocks in the solar system. Most asteroids stay safely in the belt between Mars and Jupiter, but Bennu is an Apollo asteroid, a wanderer that crosses Earth's orbit. Every 6 years it comes close to our planet, and every time it passes, gravity tugs at it, slightly altering its path. NASA has calculated the odds. There is a 1 in 2,700 chance that Bennu could impact Earth late in the next century, specifically on September 24, 2182. Those odds might sound comforting. A 99.96% chance of not hitting us seems safe. But in the high-stakes game of planetary defense, a 1 in 2,700 chance is alarmingly high. If you were told there was a 1 in 2,700 chance your plane would crash, you wouldn't get on board. And if a rock the size of the Empire State Building were to hit the Earth, it would unleash energy equivalent to 1,200 megatons of TNT, dwarfing the most powerful nuclear weapon ever detonated. It wouldn't be an extinction-level event like the dinosaur killer, but it would devastate a continent and change the climate for years. To prevent this, we need to know exactly where Bennu is going, and that is harder than it sounds. We can predict the motion of planets for centuries with perfect accuracy, but asteroids are different. They are small, light, and subject to subtle forces that push them off course. The most important of these is the Yarkovsky effect. We touched on this earlier, but its importance for planetary defense cannot be overstated. As Bennu spins, it absorbs sunlight on its day side and radiates it as heat on its night side. This escaping heat acts like a microscopic thruster. It is a tiny, invisible hand constantly pushing the asteroid. Before OSIRIS-REx, we could only estimate the strength of this push. We had to guess how rough the surface was and how well it retained heat. But thanks to the mission, we don't have to guess anymore. We have mapped the thermal properties of the entire world. We know exactly how the rocks heat up and cool down. We have measured the Yarkovsky acceleration with unprecedented precision. Because of this mission, we have refined our calculations of Bennu's orbit for the next 2 centuries. We have significantly reduced the uncertainty. We now know, with far greater confidence, where the asteroid will be in 2182. We are no longer flying blind, but knowing the path is only half the battle. If we ever did have to stop Bennu, or an asteroid like it, we need to know how to fight it. And this is where the rubble pile discovery becomes a matter of survival. For decades, science fiction has taught us that to stop an asteroid, you blow it up. You drill a hole, plant a nuke, and shatter it. Or in a more realistic scenario, you slam a spacecraft into it, a kinetic impactor, to knock it off course. But OSIRIS-REx taught us that Bennu is not a solid rock. It is a loose collection of debris held together by a whisper of gravity. It behaves like a fluid. Remember the sampling moment? The spacecraft's arm didn't bounce, it sank. The surface offered almost no resistance. This has terrifying implications for deflection. If you were to fire a kinetic impactor at Bennu, slamming a heavy spacecraft into it to push it away, it might not work the way you expect. Instead of pushing the asteroid, the impactor might just punch a hole in it. The loose rubble might absorb the energy like a sandbag absorbing a bullet. The shock wave wouldn't propagate efficiently. It would dampen and die out in the voids between the rocks. Trying to punch a cloud of gravel doesn't move the cloud, it just rearranges the gravel. This knowledge changes the playbook. It suggests that for rubble pile asteroids we might need different techniques. Perhaps we need a gravity tractor, a heavy spacecraft that flies alongside the asteroid, using its own small gravitational pull to slowly tug the rock off course over years. Or perhaps we need to detonate a device nearby to vaporize the surface and create a rocket-like thrust, rather than hitting it directly. OSIRIS-REx has given Planetary defenders the user manual for the enemy. We now know that the most common threats to Earth are likely these fragile, porous, tricky rubble piles. We know we can't treat them like solid billiard balls. Beyond defense, the mission matters because it opens the door to the future economy of space. The water and organic molecules found in Bennu's dust are not just scientific curiosities, they are resources. Water can be split into hydrogen and oxygen, rocket fuel. If we are ever to become a spacefaring civilization, we cannot launch all our fuel from Earth. It is too heavy and too expensive. We will need gas stations in the void. Carbonaceous asteroids like Bennu are the gas stations. They are the hydration stops. By proving that these rocks are wet, containing water trapped in clays, and by proving that we can successfully navigate to them, touch them, and leave, OSIRIS-REx has laid the groundwork for asteroid mining. It has shown us that the materials we need to explore the outer solar system are waiting for us in the black. Ultimately, this mission matters because it replaces fear with knowledge. Before this, Bennu was just a shadow and a statistic, a dark rock with a scary probability attached to it. Now, it is a place. We know its valleys, its boulders, and its chemistry. We know how it spins and how it drifts. We have held it in our hands. We have turned a monster into a map. And in the vast, indifferent darkness of the universe, that knowledge is the only shield we have. In a quiet room in Houston, inside a nitrogen-purged cabinet, sits a small pile of black dust. To the casual observer, it looks unremarkable, like something you might sweep off a driveway or shake out of a hiking boot. But this dust is older than the ground we walk on. It is older than the atmosphere we breathe. It is older than the biology that allows us to see it. The OSIRIS-REx mission was a feat of engineering, navigation, and planetary defense. It was a loud, fiery, complex endeavor involving rockets, lasers, and autonomous robots. But now that the noise has faded, we are left with something quiet. We are left with a connection. When we look at those white crystals of magnesium sodium phosphate crusting the dark rocks of Bennu, we are not just seeing a mineral, we are seeing a ghost. We are seeing the dried up residue of an ancient ocean that existed before the Earth had finished forming. We are seeing evidence that the dark, cold void of space was once wet and alive with chemistry. It forces us to confront a profound realization. We are not separate from the asteroids. We are not distinct from the rubble piles drifting in the dark. We are part of the same story. The water that flows in our rivers, the carbon that knits together our DNA, the phosphorus that powers our cells. It is very likely that much of it was delivered by rocks just like Bennu. When we look at that sample, we are looking at our own baby pictures. We are touching the seeds from which the Garden of Earth grew. This is the ultimate message from deep time. It tells us that the separation between us down here and space up there is an illusion. The Earth is just a collection of space debris that got lucky. We are the rubble that woke up. There is also a profound humility in how this mission ends. You might think that after 7 years of work and $1 billion of investment, the scientists would rush to analyse every single grain of the sample. You might think they would grind it all up, dissolve it in acid, and run it through every machine they have to wring out every secret immediately, but they didn't. The team made a decision that speaks to the very best of human nature. They decided to study only a quarter of the sample. 25% of the material is being analysed right now by researchers around the world, but the remaining 75%, the vast majority of the treasure, has been sealed away. It has been catalogued, packaged, and placed in a vault for the future. Why? Because the scientists of today know something important. They know they are not the smartest people who will ever live. They know that technology is accelerating. 50 years ago, during the Apollo missions, astronauts brought back moon rocks. At the time, we didn't have the technology to analyse them fully. We saved them. Today we're opening those Apollo samples and finding things that the scientists of 1969 could never have imagined, using instruments that didn't exist when the rockets launched. The OSIRIS-REx team has done the same for Bennu. They have saved the sample for a generation that hasn't been born yet. Somewhere, perhaps in a kindergarten class today, or perhaps not yet born at all, is the person who will make the greatest discovery using Bennu's dust. They will use a machine we cannot conceive of to ask a question we haven't thought to ask. This act of preservation is an act of hope. It is a declaration that there will be a future, that there will be science, and that there will be humans curious enough to keep looking. It turns the sample from a scientific specimen into a gift, a message sent from the past, the asteroid, to the present, us, and forwarded by us to the future. As for Bennu itself, it is still out there. The spacecraft has left. The asteroid has returned to its lonely silence. It continues its spinning, drifting journey through the dark. It will continue to crack in the cold and shed rocks into the void. It will continue to feel the gentle push of the sunlight and the tug of the planets. But it is no longer just a stranger in the dark. It is a world we have touched. In the year 2182, when Bennu makes its close approach to Earth, the people living then will look up at it not just with fear, but with recognition. They will know its density. They will know its history. They will know that it is a piece of the ocean that made them. And perhaps on a clear night you can look up too. You won't be able to see Bennu with your naked eye. It is too small and too dark. But you know it's there. You know that in the vast infinite blackness, there is a small spinning diamond that has given up a piece of itself to help us understand who we are. The universe is vast and the distances are breakingly large, but for a brief moment we reached out across the void. We tagged a falling rock. We brought a piece of the beginning to the end of the journey. And in doing so, we reminded ourselves that we are explorers, that we are capable of patience, and that even in a universe of rubble, we can find something precious. The robot is gone, the dust is safe, the story continues. Good night.